Welcome everyone to our second unit in the Physics C Electricity and Magnetism course. So first of all, there are some basic concepts covered in the Physics 2 video that I'm going to let play right now. We have electric potential, capital V, also known as voltage. Okay? Electric potential has units of joules per coulomb. You'll notice why those units are important in just a moment. Okay? Let's say, again, that I am dealing with a charge of plus 10Q. I'm going to come back to this demonstration in just a moment. Let's go back to voltage right now, or electric potential. Your electric potential is, again, given by your constant times your charge Q, which will be your central charge that you are dealing with, divided by the distance from that central charge. Okay? Again, potential is evaluated at a particular point. And like electric field, electric potential has isolines, lines at which the electric potential are always constant. Even though electric field and electric potential both have isolines, the electric field isolines are not the same as the electric potential isolines, even though they look the same. In AP Physics 2, anytime you are asked to draw isolines, it's always going to be the electric potential isolines. Anyway, let's move on from there. Electric potential is a determinant of the potential energy of a particle at a given point. Okay? So again, let's draw our electric potential isolines, and electric potential is not a vector, therefore you cannot draw electric potential vector lines. Keep that in mind. Electric potential is not a vector. If I were to put a positively charged item right there, it would have a lower electric potential than if I had a positively charged particle right here, because electric potential is inversely proportional to 1 over r. They're directly proportional to 1 over r, inversely proportional to r. Okay? So as I get further away from the charge, my electric potential decreases, and therefore my electric potential energy decreases. So let's introduce that equation. Your change in electric potential energy is equal to your charge times your change in electric potential, or your change in voltage. Potential energy being in units of joules, charge being in units of coulombs, electric potential being in units of joules per coulomb. We can see why that makes sense. Change in voltage is not a vector because energy is not a vector. Electric field is a vector because force is a vector. And that is the relationship that they have to each other. One is a determinant of the other if you provide a charge into the equation. Now, understand that these equations can also work for the opposite charge. If I have a negative charge that is placed right here, the negative charge will want to move towards the positive center. So that negative charge, since it has a negative Q, will result in a negative potential energy. Since the electric charge will be moving this way, change in potential equals final potential minus initial potential. So we discussed that potential is always greatest nearest to the center. So if a particle moves this way, closer to the center, then your change in potential is positive, because your final is greater than your initial. What kind of particle would be moving this way towards the center? That would be a negative particle. So a negative charge Q times a positive delta V would equal a negative change in potential energy. And the inverse is true for the positive particle. For a positive particle, you are being repelled, you're moving this way. Your final electric potential is less than your initial electric potential, therefore your change in electric potential is going to be a negative. So given that your change in electric potential is negative for a positive charge, you can say that your change in electric potential energy is going to be your positive Q times your negative delta V, meaning your change in potential energy is still a negative. It's a negative for both cases, whether you put a positive charge or a negative charge there. Why is the change in electric potential energy always negative? Because your electric force will always act on the particle to accelerate it. the electric force will always act to do work on the particle, right? It's the same as, why does your gravitational potential energy always decrease if nothing is holding you back? Because your gravitational force will always act to do work on a non-stationary object. Which means if I place a positive charge right here, these two charges are going to repel each other, and the charge I placed right there is going to gain kinetic energy. Where is it going to gain the kinetic energy from? It's going to gain the kinetic energy by a loss in electric potential energy. And the inverse is also true. So one of the topics we saw in that was the concept of electric potential energy. And that was given to you by the formula K, Q1, Q2 over R. And now that we're able to use calculus to analyze this, we can enable ourselves a greater understanding of why this equation works by doing the work integral, okay? We know that the electric force, F sub E, is equal to K Q1 Q2 over R squared. So if we do the work integral by that force, the best way to imagine it is, let's say I have some point charge of positive sign, okay? And if I have a positive point charge and I were trying to analyze the potential energy of another positive point charge that is at some distance r away from it, since there is a repulsive force between these two charges and I want to integrate over that force, I would ask myself, how much energy would I need to input? How much work would I need to do against the repulsive force if I wanted to bring this point charge from infinity to, if I wanted to bring it in from an infinite distance away and I wanted to bring it in so that it is at this radius, okay? Because as we know by this equation, the electric force continues to act on any particle up until they are an infinite distance away, and that is one of the assumptions made on your reference table. The electric force felt by any point charge at an infinite distance is 0, okay? So we're basically trying to integrate from when our force starts, which is infinite distance away, and we're trying to finish integrating when we are at our desired distance r, okay? So therefore, our bounds of integration from the work integral would be infinity to r of k q1 q2 over r squared, okay, dr. And that would be a negative k q1 q2 over r, okay? That's our integral, and we're going to evaluate it at the bounds of integration, okay? But there's one small problem. We must remember that the work integral is a dot product, okay? So we need to analyze what that dot product does to our equation, okay? First of all, the force vector, being a repulsive force, is pointing, let's say, downward in this case. And I'm trying to pull the particle out from infinity upward to this distance r. Therefore, my displacement and my force are in opposite directions. Therefore, my cosine theta, my dot product, is going to resolve to -1. So the negative that resulted from my integral and the negative that resulted from my dot product both cancel out. Therefore, I'm just left with this. So first we evaluate at infinity. Since this is an improper integral, we're going to need to take the limit. So the limit of any constant c, which in this case is a constant, these three values are constant, over r as r approaches infinity is 0. So therefore, the bottom bound does not contribute meaningfully to our analysis. So we're just going to evaluate it at the top bound, k q1 q2 over r. And that's how we derive the equation for electric potential energy. Reminder that potential energy is a scalar and not a vector. So from there, let's review another concept covered in that little clip, which is electric potential, often denoted as capital V, okay? Our capital V is given the equation K Q over R, okay? For a discrete system, it would be V equals K times the sum of Q's divided by their radiuses, and for a continuous system, it would be K times the integral of a differential charge over its distance from a reference, okay? before we get into the calculus, I wanted to give us all a very definitive analysis of what these four variables mean, okay? So we're dealing with four variables that we might not have a complete grasp on. We have force, electric field, electric potential energy, and electric potential, okay? It's useful for us to understand particularly what all of these mean because their equations are so similar, okay? Electric force, I think, is the easiest to understand. It is the repulsive or attractive force, depending on the charges, that exists between any charges, okay? You can see here that at any distance r away from an amount of charge, there will be a repulsive force between like charges and an attractive force between unlike charges. The electric field is analogous to your acceleration, okay? The electric field is basically a quantity where you would multiply by the electric field times your charge, and this would therefore give you the amount of force being felt. It's analogous to you multiplying your acceleration times your mass to give you the force being felt. Okay, electric field is best conceptually understood as your electric acceleration, okay? If you have an electric field pointing in one direction, it means if you drop a charge there, if you multiply by a charge, then that charge will be accelerated in the direction of the electric field because it is applied an electric force. Now, a similar analog is found for electric potential energy. I think we can conceptually understand electric potential energy if I have two particles a distance apart, and let's say they are the same charge. That means they're going to want to repel each other. So if I release them from rest, they're going to repel each other and gain kinetic energy. Therefore, there must be stored electric potential energy, and the opposite is true for opposite particles. If I release them from rest, they will begin to fall towards each other and gain kinetic energy. So the formula for electric potential energy, as I've written up here, is K Q1 Q2 over R. Okay, and your voltage, your electric potential V, is analogous to how much potential energy a charge would have, okay? So if I take my electric potential at a point and I multiply it by any charge, I multiply it by a charge that I put there, then I would get the electric potential energy of that charge, okay? It's very useful to consider this in terms of a diagram, okay? If I were to have a point charge, let's call it plus Q, this point charge would exhibit an electric field, okay? And that electric field would point outwardly from the charge, okay? Because we always analyze electric field lines and vectors and all of this as if we are dealing with positive charges. So your vector lines will always be drawn in the direction that a positive charge would move or drift or accelerate, okay? So these lines represent our electric field. Meaning if I were to drop a positive point charge at this point, I would calculate the electric field at that point, and I would multiply the calculated electric field by the charge that I dropped at that point, and that would be the electric force felt by the charge. Consequently, you have electric potential isolines, meaning that if we take a look at potential energy, your potential energy is greatest near the charge, and it decreases the further away you get from the charge for positive particles, okay? So this would be maybe plus 10 volts, this would be plus 8 volts, plus 6 volts, plus 4 volts, plus 2 volts, and so on and so forth. It wouldn't decrease linearly like that because we're proportional to 1 over R, but you get the idea, okay? And the reason I'm saying plus is because we have a positive voltage because we're dealing with a positive charge. If I had a negative Q, I would say minus of 10 volts, minus 8 volts, etc., etc., okay? So the important thing to recognize here in this diagram is that your isolines, your circular lines, your potential lines, equipotential lines they're called. Why are they called equipotential lines? Because every point on an equipotential line has the same potential, has the same electric potential. What the isolines, the electric potential lines, tell us is if I were to drop a positive point charge plus Q right here, I would take the electric potential at that point, I would multiply it by the charge I just dropped there, and that would give me the electric potential energy at that point, okay? Electric field is a determinant of the electric force felt. Electric potential is a determinant of the electric potential energy, okay? Also notice the difference here. Electric field is a vector, so it is a determinant of a vector force. Electric potential is a scalar, so it is a determinant of a scalar electric potential energy. Something important to realize here is that for any point in your graph, whether it be explicitly stated like this or imaginary or implied, your electric field vector is always perpendicular to all electric potential isolines, okay? The reason for that being is because in order for an isoline to be an isoline, in order for electric potential energy to be constant everywhere on the isoline, there can be no work done at any point on that isoline, okay? What is the force that would be doing work in this case? The electric force, okay? Therefore, the electric force must always be perpendicular to the isoline, so that if we do the dot product in our work integral for energy, the dot product is always zero, because in order for potential energy to be constant, work done must be zero. That's why keeping constant potential energy must be exactly perpendicular to our electric field vector, which is a determinant of the force vector. Now let's move on to some of the other equations you've been given here. First, we need to look at this, okay? The calculus example or expression of electric potential, okay? Now, electric potential is very easy if you understand how to derive electric field at a point from the previous unit, okay? If I take my electric potential equation in the integral form, and I write it right here for you guys, I'm going to compare it to the electric field integral equation, which is the integral of dq over r squared, okay? We can see why these equations are so similar. It's just a difference of r versus r squared, okay? So if I were to bring back up the practice problem I gave us in the last video, I'm going to put a picture of that right here. You can see that when we did the electric field contributions by charges in the ring, we needed to do a bunch of complex derivations, and we needed to differentiate between what were our variables and what were our constants. And if you're unsure how to do this, or if you're fuzzy, please rewatch that section of the previous video, because this is very important stuff right here. This part of Unit 1 in particular is very, very, very commonly one of your FRQs, so I'd brush up on this if anything. Anyway, the same exact process that you used for electric field can be used to determine electric potential, okay? The only difference here being that electric potential is a scalar, so you won't have vector components canceling out, as we did in the previous analysis. If you guys ever need help solving problems like that, just join the Discord server. I'd be happy to pull up a practice problem and help you work through it. They're much more commonly found, these really complex calc problems like this. You're very much more often going to see them with electric field instead of electric potential, but we can see why the process is extremely similar, because you would just be exchanging r for r squared in your final equation. Also, let's cover some of the rest of our equations in our reference table, such that the next one we're looking at is that the change in electric potential, the change in voltage, equals the negative times the integral from a to b of the electric field dotted with the displacement vector, okay? And we can see how that is applied right here in this diagram, okay? Your change in electric potential, your traversal across these isolines, is equal to a change in the electric field. And since the electric field is changing as it is traversing across this line, we're going to need to use the integral to determine the precise change in electric potential. So why is this a negative? Okay, well, first we need to discuss that the change in voltage is equal to the voltage at the final position minus the voltage at the initial position. Your electric field at this point right here is going to be less than your electric field at this point right here. Okay, so if you have a positively charged particle placed in this diagram I've drawn for you, if let's say that the electric field is pointing outwards in this direction because we have a charged particle, and I place another charged particle here, then the particle will begin to accelerate along the electric field, okay? So in that particular example, the electric field pointing in this direction would be in the same direction as the displacement, also going in that direction. Therefore, our dot product would evaluate to +1 because our electric field and our displacement are in the same direction. However, as we get further away from the point charge, our electric potential decreases, okay? So in order to resolve a positive integral here, we need to add a negative to say that when we have a positive traversal of the electric field, we have a decrease in electric potential, okay? Given this equation, we can deduce from our calculus understanding that the next equation on our reference table, the electric field in a particular direction, your reference table references the x direction, is equal to the derivative of electric potential with respect to x. Also, it's the electric field in the y direction is the derivative of electric potential with respect to y, and so on and so forth for the z direction. Okay, you may need to analyze this derivative in multiple dimensions, so be prepared for that. Okay, next and finally, the easiest part of this unit is conservation of energy. And since all of you have taken a mechanics course before, you are very well acquainted with conservation of energy. Okay? The next equation on your equation sheet has been just something I've shown you right here, which is that your electric potential energy, or rather your change in electric potential energy, is equal to your charge Q times your change in electric potential. Okay, I wrote it as your electric potential energy equals QV, but they are roughly equivalent. The general application of conservation of electrical energy. We are going to observe this much more in depth when we cover circuits, but for right now, the only electrostatics applications we're going to see of this is if I have, let's say, 2 point charges. Let's call it a positive charge and a negative charge because I don't often do opposing examples. They are separated by a distance r. Therefore, their electric potential energy would be calculated via this equation, and in this case, it would be negative because you have a positive times a negative. And that, since they're at rest, the total energy of our system would be our electric potential energy, given by that equation. And then at some time t after we have released them from rest, they will have traveled some distance x, such that their new displacement is now, I'm going to call it R2, where this original displacement was R1. And we're going to say that the electric force equals K Q1 Q2 over R squared. We're going to say that that electric force acted on a distance dr from R1 to R2. And we have our force integrated with the dot product of our displacement vector, giving us work. And so from here, now you know the work done on one particle by the other, so you can calculate the kinetic energy of the system, which would be equal to this work done. And their kinetic energy, in addition to our remaining potential energy, would therefore equal the original total energy of the system. Okay? Simple conservation of energy problem. Thank you, guys.